everyone, and welcome to Talk Nerdy. Today is Monday, December 19th, 2022, and I'm the host of the show, Cara Santa Maria. So I'm wishing all of you a very happy holiday. This is our last show of the year. It's actually our last show before we go on hiatus for 2 weeks, as we always do around the holidays. So we will see you again on January 9th with our first episode of 2023. What? Let's not think about that right now. Instead, let's just get excited about an awesome show. But before we dive in, as always, I want to thank those of you who make Talk Nerdy possible. Talk Nerdy would not exist without support of listeners just like you. I know it's a tough time because of the holidays. I really, really hope that you are putting yourselves and your family first. If you are able to give, the way to do it is by visiting patreon.com/talknerdy. But of course, and again, I really do hope that you're able to prioritize all of the things that you need to prioritize in your lives right now so that you have a happy and a healthy holiday. I know the holidays can be a lovely and beautiful time. They can also be a very hard time for a lot of people. So for those of you who either don't have families, are missing somebody in your family, are away from your families, or are struggling within your families and or your chosen families, I want you to know you're not alone, and I'm thinking of you. I do want to give a shout out to our top patrons this year. They include Daniel Lang, David J.E. Smith, Mary Neva, Brian Holden, David Compton, Gabrielle F. Jaramillo Gonzalez, Joe Wilkinson, Leonard Prince, Pasquale Gelati, and Ulrika Hagman. Thank you all so much for always supporting the show throughout 2022 and beyond, and for everybody else who has pledged their support over the many years that we've been together now. I really do thank you from the bottom of my heart, and I'm just so very grateful for you. All right, so I've got a good one for you guys, and I don't often read the full bio of a guest, but hers is so impressive. I don't know how to summarize her without reading, not the whole bio, but a fair amount of it. So I had the honor to sit down this week with Dr. Feryal Özel. She is the chair of the physics department and also a professor in the School of Physics at Georgia Tech. Before that, she was an astronomy and physics professor and associate dean for research at the University of Arizona. She did her doctorate at Harvard. She also has previously studied at Columbia, the Niels Bohr Institute. She was a NASA Hubble postdoc fellow, a member at the Institute for Advanced Study at Princeton for a while. She has so many appointments. She's a fellow of the American Physical Society. She was elected to the Science Academy of Turkey, and she has won so many incredible awards. I'm going to read some of these to you. So because of the incredible work that she's done, she was awarded the Maria Goeppert-Meyer Award from the American Physical Society, the Guggenheim Fellowship, the Radcliffe Fellowship at Harvard, a Miller Institute Visiting Professorship from the University of California at Berkeley. And along with the Event Horizon collaboration, she was awarded the Breakthrough Prize, the Rossi Prize of the American Astronomical Society, a Diamond Achievement Award from the National Science Foundation, and she was recognized with the distinction of Breakthrough of the Year by the journal Science. Yes. Big deal. We're going to talk about her incredible work right here on Talk Nerdy. So thank you all for joining me. Thank you for being here throughout the year. And a big thank you. Here she is, without any further ado, Dr. Feryal Özel. Well, Feryal, thank you so much for joining me today.
Thank you for inviting me, Cara.
I'm excited to talk about so many things, astrophysics, so much interesting research that you've done throughout your incredible career. And of course, you've recently had a big career move. So I guess before we dive into the work that you've done, I'm curious, you are now at Georgia Tech and you are chairing the Department of Physics. What was that experience like for you, making that transition?
Well, it's still a transition. I only moved a few months ago. So maybe if we connect back in a year or so, I'll be able to tell you more about what this experience is like. But joking aside, it's a really fun opportunity for me to not only do my own science with my own research group and the collaborations, but set up a system where others can do exciting science and connecting them with opportunities, thinking more about the students through the arc of their careers, from our graduates to our PhD students to postdocs. So it is a slightly different way of looking at things. And Georgia Tech was exciting for me because I do a lot of computational astrophysics and a lot of digging into data. And there are strengths here that aligned with what I do. I feel like it was a natural fit and a new adventure. So that's what I'm doing.
And you have really been, I mean, obviously we're going to talk about the work, but just in terms of like geography, you have studied and done research all over the place, right? Can you kind of take us on a little journey from maybe your early education until now, like where you've been throughout the way?
Sure. Yeah, it is. It is definitely a bit of an immigrant story, but also a little bit of an academic story. So I grew up in Istanbul, Turkey, and I went through high school there. I had a wonderful experience actually in my middle and high school, which is I know is rare. Um, and at the point of looking at colleges, I knew because of partially my high school, I knew that studying abroad was an opportunity for me. So I applied to some schools in the U.S. and ended up going to Columbia University in New York for my undergraduate degree in physics and applied mathematics. And after that, I was basically geographically not super committed yet, and I wanted to do particle physics. And I spent a summer at CERN, the particle physics laboratory in Switzerland. And at the time, I thought, okay, if I want to do particle physics, Europe might be a better place to be. So I went to Niels Bohr Institute in Copenhagen for a year, got my master's degree there. And at the time, then realized, yes, I'm interested in fundamental physics problems. And I would like to really figure out the mysteries of how things work at a pretty basic level. But astrophysics is a better venue for doing that at the time than particle physics because of, it was between the two large experiments at CERN, the Large Electron Positron Collider and now LHC. The opportunities were fewer. Certainly, the data coming from astrophysics was far more in volume and in excitement. Mm-hmm. So I went to Harvard for my PhD in astrophysics. So those are my schooling years. And after I finished my PhD at Harvard, I went to the Institute for Advanced Study at Princeton as a member and as a NASA Hubble postdoctoral fellow. And from there, I moved to the University of Arizona with my faculty position, which I actually did end up staying for quite some time.
How long were you in Arizona?
Almost 19 years.
Oh, wow. Yeah. Okay. So this was a big change coming over to Georgia then. 19 years in Arizona before this.
It is. Yeah. I mean, I think it's... I was only 17 when I left from Istanbul. So, and of course, some of those years I can't even remember. So certainly as an adult, I spent the majority of my life in Tucson, Arizona. And I loved many aspects of it. But in academia, I think partly we tend to go where new ideas and directions take us. Good or bad, some people love moving, some people don't appreciate moving as much, and moving for your postdoc and then for jobs. But I do like it. Yeah, so that's been the arc so far.
Yeah, it's interesting because when I look and I see this quite often with academics, and as you mentioned, especially very often in physics, sometimes in kind of like evolutionary biology, ecology, academic appointments that require a lot of field work or that require a lot of collaboration, that your bio is like, okay, you were here doing this, you were there doing this, you were there doing this, then you were there doing this. But along the way, you were also the,
Mhm.
working on this collaborative project, doing this for NASA, doing this over here for this telescope. And it's fascinating to see how it's not just about where you are and what questions you're asking within your quote lab, but it's also about these big collaborative projects that you have been a part of.
Absolutely, you hit it right on the head. I think an academic could limit herself or himself to only the things they're doing in their own office or in their own lab. But very often, that's not how we work. We work across institutions. We work with federal agencies such as NASA in my career on different projects. Sometimes they take decades, and sometimes it's a particular role that you serve um, in getting something off the ground or on a committee. And again, more often than not, the collaborations can be quite large. Certainly, in some fields, astrophysics is going in that direction of in order to get the high quality data that we need the resources that we put together across institutions, across countries, and in the case of the Event Horizon Telescope, across continents. So it's true. I mean, they're almost like two parallel CVs, right? One is where are you in terms of what your position is. Are you a professor here or there, or are you a fellow somewhere? But then the other parallel path is what does your research actually look like, and where has that taken you? And so that's been pretty diverse for me as well.
Yeah, so I guess that is a good entree into making that connection because we've talked a bit about where you were geographically and what your positions were in those different institutions. But now let's maybe talk about the evolution of your research. You touched on it a little bit early on, this sort of difference between focusing your efforts between astrophysics and particle physics, of course, of which there's so much crossover, just in terms of your career ambitions and the state of the state of the literature, the state of the research, the state of the zeitgeist within physics at the time. So maybe you can tell us a little bit more about that. Maybe we can start by even defining or describing the difference between astrophysics as a term. What does that really describe, and what specifically is particle physics?
Sure. Astrophysics basically is the physics of all the phenomena that we see in the universe. Our data come from typically telescopes. Sometimes these are telescopes based on Earth, sometimes they're telescopes in space orbiting around the Earth or other objects. And we collect data at different wavelengths of light about things happening in the universe. Sometimes it's an open ended question. Let me just look and see what is happening. These are sort of surveys. But sometimes one designs an instrument or a telescope specifically to answer a certain question. And for example, the cosmic microwave background experiments and the Event Horizon Telescope that I'm a part of, it is more a specific goal of making a measurement and trying to understand what that says about either how the universe evolved or about how stars form and die, about black holes and their environments, and many other questions. So astrophysics is the discipline where we use the physics that we know from every domain, the the particles, the interactions, fluids, radiation, and we put together models for um, what we see in the universe and use it to understand them.
Mm-hmm. And so where have your interests sort of been and shifted over the course of the changes within the physics community, the new technologies that have actually the whole new physics, right? Like we have things like gravitational wave astronomy that like literally did not exist when you were in training. So, or at least
Absolutely.
wasn't functionally existent. It might have been
Right.
theoretically existent.
Uh-huh.
Yeah.
The ideas.
And right. So like how have your sort of interests evolved over the course of your career? Maybe you can take us a bit on a timeline story of what you were originally studying, what questions you were trying to answer, and how that's changed against the background of the changing science.
Yeah, it's interesting. Once I decided that astrophysics is the right domain for me, I still brought some questions of what happens in extreme environments. How can we understand, for example, the physics of matter at extreme densities, the physics of matter in extreme gravitational fields, physics of matter in extreme magnetic fields? Do Are there qualitative changes? Are there new states of matter? Do the interactions happen in a way that is not described by our current theories from laboratory experiments or existing astrophysical measurements? So I was always drawn to that frontier, that boundary of, one could say, almost like breaking things, but breaking things only in the sense of, is our understanding complete? Do our theories, how we formulate interactions between things, are they sufficient to describe what we find in those environments? And that naturally took me to study two types of objects in the universe. One is black holes, where we can't even talk about matter in its normal sense anymore. There isn't a surface or a density or really an object to talk about. It is an infinite energy density that has very peculiar properties. And then you can ask, how does matter behave around it? Is gravity what we understand it to be from Einstein's theories, etc.? And the second type of object that it has drawn me to are neutron stars, which I like to call cousins of black holes. There is still a mass, something with a surface, something that emits light, that is more familiar to our everyday experience, but it is in such a dense form that we don't quite understand what happens to building blocks of matter like nuclei in their interior, and they can possess magnetic fields that are so strong. I mean, literally billions of times stronger than what we see in our sun, for example. And then we try to understand, or I have tried to understand the impacts of those extreme densities and magnetic fields on the properties that we can observe from neutron stars. So those are the two themes, sort of, in what I have done.
I'm curious, and this probably isn't a question that you can answer specifically, but for those listening who, like myself, am really interested in the relationship between theoretical astrophysics, the mathematical modeling that takes place, within the I always use the word lab to denote what's going
Yes.
on within the sciences, but of course, very often a theoretical lab may just be a computer or maybe many computers tethered together, or sometimes
Yeah.
even pencil and paper. But the sort of relationship between the theoretical components, the mathematical modeling and theorizing, and the actual direct observation, and how they feed into each other. Like, I think I can imagine a situation in which we see things with our telescopes, with our, whether it's a radio telescope or a visible light telescope or an X-ray, whatever. And then we try to understand them mathematically. We try to understand them theoretically. And then we make new observations and iterate on these models. But it's not quite that simple, is it?
Well, I think iterate is the key word here. It may not be simple. It's definitely not linear. It's not like I do one thing, then my observer colleagues do another thing, and I do one thing. But there is certainly a dynamic there that is iterative, and sometimes the theoretical ideas lead and they guide the development of experiments, and other times one does a set of experiments or observations. There's a brand new phenomenon that you didn't even think about or expect, and then you go back to the drawing board about and ask, why is this happening? What is this? So the iteration is always there, and as I said, sometimes, for example, the ideas behind our theory of gravity, general relativity, there were some observations that in the beginning of the 1900s that indicated that Newton's theories didn't quite describe it correctly. Like we knew about, I mean, I wasn't alive, but scientists at the time knew about the precession of the orbit of Mercury and that it didn't obey what Newton did. But it wasn't trying to understand that discrepancy between the existing theory and the observations that led to a brand new theory of gravity, which is Einstein's theory. It is really starting to think about space and time in a different way. Same thing with black holes. Black holes are a prediction of that theory. It's not because we had a bunch of observations and evidence that we didn't know what to make out of, and then we said, oh, these must be black holes. On the contrary, black holes existed as an abstract theoretical idea, and we worked out many aspects of it as a community before we even had the first observation. So there are times when there is a paradigm shift, a framework shift, just because of new ways of thinking about mathematically or physically about our universe. And other times, cosmic microwave background. You set up an antenna, you look at the sky, there's a signal there. You're like, what is this? And then you realize, oh, that's the relic radiation from the Big Bang. And then an entire beautiful theory stems from it and develops into modern day cosmology. So, so there are unexpected relationships, let's say, between theory and experiment that go in either direction. One leads or the other leads. And then oftentimes, once you have a theory in place, you go and get more data and say, okay, here are my predictions. Is it right? Is it complete? And sometimes they are, and sometimes they aren't. So the iterative process starts.
So maybe we can speak a little bit, because I know that you've sort of hinted to it, about the Event Horizon Telescope collaboration, about the images that came from that. Now I'm like, I've lost all sense of time because of COVID, but this happened during COVID, right? Or was it right at the beginning?
Well, the first set of images that we released was just before in 2019.
Okay.
And the second set of images we released from the black hole at the center of our own galaxy was just earlier this year, May of 22.
Right, right. And so for those listening, to kind of jog your memories a little bit, or maybe now is the time, if you're near your phone or your computer, to look up these images so that you know what we're referencing here. This is kind of a beautiful example of exactly what you were describing, the way that sometimes observation then sort of feeds back in to, or observation comes first, but other times there's been so much theorizing, so much modeling, and we've never actually been able to directly observe any of these things, at least not visibly. And then here we are, only a few years ago, with this stunning image that the entire world could appreciate in a way that I'm not sure those of us who are non-physicists could have ever marveled at a page of, math in the same way, because we can't read that language. We read the language of images.
Right. I appreciate that, although I love the math too.
Right.
Yeah, so this is indeed a story over decades, and it starts in the 70s, actually, before my time, when groups of scientists really tried to understand what different characteristics of black holes would be. Would they be stable? Would they emit gravitational waves when they interact? What are certain mathematical properties of matter circling around them? So that is really a push that starts in the 70s. But as we accumulated more data in the intervening decades, in the late 1990s, around 2000, we started to be able to describe the dynamics of the gas around them, and how we're talking about matter now that's falling into the black hole. It comes from maybe a nearby star, from a gas cloud, and under the influence of the gravitational pull of the black hole, it's making its journey towards it. And how does it move? How does it shine? The light, of course, doesn't come from the black hole itself, but from this material that is shining as it gains more and more energy as it's falling towards the black hole, and becomes very hot, and we see lights emitted from that. So those are the critical years where we started understanding, okay, so this is not, of course, black holes exist everywhere in the universe. We now know that. But not only do we know black holes exist, but we started being able to make physical models of the gas and light around them. And it also goes hand in hand with, of course, the push in computational physics, where we are not limited to just writing analytical models for things, but we can write down complex equations and solve them on computers for long periods of time to study, for example, long-term behavior, and make predictive models. I think the closest thing our listeners might be familiar with are climate models, where you put in different physical ingredients and there are some unknowns, and you try to make predictions. It turns out black hole environments in some ways are actually easier than predicting Earth's atmosphere. So around 2000, myself and some of my colleagues at Harvard and also elsewhere started really thinking about, what does a black hole look like? Would we be able to get an image of it? And if we did, would there be certain signatures that would tell us, yes, this is a black hole? And what wavelength of light would we have to do these observations in? We alluded to that briefly earlier on. Different telescopes see different wavelengths of light. I mean, anything from visible, which is what we see, just better, to infrared, which is our JWST telescope, launched last Christmas by NASA, to Chandra X-ray telescope that literally has X-ray vision and collects X-ray photons from the universe, to radio telescopes like big dishes, or depending on the wavelength, the telescopes have different appearances. So I started asking with some colleagues the question of, what would it take to see down to that point of no return that is that defines a black hole? And so certainly observational efforts in terms of increasing the resolution of what we see were happening, and then these theoretical ideas came on the table, saying, well, this is what we would need to set up to see down to the horizon of a black hole. And the two co-developed for the next, I would say, 20 years to make the Event Horizon Telescope happen.
So as somebody who's been on, the side of the research of black holes, really trying to understand exactly what is going on um, around and within these incredible phenomena, when the images were finally, I guess, produced, I'm not really sure the right way to put it. I mean, they weren't really, quote,
Produced is good,
captured.
yeah.
Right, yeah,
Yes.
because obviously there's a lot of processing involved and a lot of different kind of lines of evidence involved to produce these images. But when finally they were ready, or maybe throughout the course of getting them ready, was there anything that surprised you? Was it just kind of exactly what you expected? Or were there aspects of this visualization that made you think differently about your own work?
Thank you for asking this question. It's been mixed.
Okay.
Was it exactly what you expected versus are there surprises? So the first surprise was that the experiment worked.
Right.
Just seeing the images, or even before we made the images, there were certain aspects of the raw data that immediately signaled to us that this is what we were expecting to see in the when we combined signals from various telescopes and it had a certain pattern. We thought, oh my God, this worked. How is that possible? We were surprised with how did this work? How is it possible that what we envisioned actually came true? But apart from that, we were actually surprised with how well our models did in terms of predicting the um, basic signatures of that image. The hole in the middle, how big would that be? The what we like to call the donut, that bright part, the ring of light around that dark center. Again, its basic properties. We got it pretty well with our combination of sophisticated like supercomputer models and our understanding of what the gas does and our understanding of how gravity works. So when we got the second image, that was further confirmation that the gist of what we're doing is right. But then with the second black hole, we actually encountered something that is more of a surprise, more in the unexpected domain. And that is, how quickly does this image change? And you might ask, why does it change at all? I mean, why does gas that's around a black hole look different one day from another? Our expectation was that as this gas swirls around the black hole, it's a turbulent system. It's like bad weather, right? Like things are really clouds forming, coming, going. And in that particular case, actually, the magnetic field structures are changing. So, based on our modeling, we were expecting a lot of change from hour to hour, day to day, to the extent that we thought with the second black hole that has a faster time scale for these changes, the experiment might not even work. But not only did it work, it showed that this weather, in quotes, was far less than most of what our models predicted. So that is a very nice little glimpse for us into what aspects of this turbulent, what we like to call plasma, because the temperature is so high that the electrons are stripped from the nuclei. I mean, from the atoms. So there we have the ions and the electrons separate. It's a soup, and this is giving us new directions as far as what it is that we should be looking at.
And so,
In
I mean, is it safe to say then that they are more, I don't know how to put this, but like stable than you expected?
Yeah, it's calmer.
Okay.
It's not moving in a violent way like we expected. We thought as this gas is swirling around the black hole, making its way into the center, that we would constantly see flickering and maybe even like larger scale changes where one side is brighter than the other side is brighter. Tubes of like filaments light up and disappear. Most of our models, like any simulation that I showed for the last 10 years or so, and these are expensive simulations, computationally speaking, there was a lot going on. And when we looked at the real data, it's a lot calmer.
Is that a function of just like a mismatch between the data and the observation, like whatever calculation errors, things of that nature, or is it a function of the resolution at which we're actually observing these things, like time scale? If we had a larger kind of data band and we're able to look for over longer periods of time, would they be a little bit more violent and tumultuous?
That's a great question. In the particular case of the black hole at the center of our galaxy, Sagittarius A star, the time scale for the natural physical time scale for these changes is anywhere from hours to days.
Okay.
So we're looking right in that comparable to the time scale of our experiments.
Mm-hmm.
So that's why we were much more worried about that black hole than the black hole in M87, which has a much larger mass. It's about 6 billion times the mass of the sun. So things move much more slowly around that. So in that case, we thought, okay, we don't expect things to change over the 10 days of observations. So it's not that we're lucky. Maybe if we looked at it the year after, it would be different. Whereas with Sagittarius A star, we actually have the right time resolution to be asking this question. So it's not an error in the calculation so much as something we don't understand about how particles are behaving in that environment. And
cool.
I don't know.
So still
Yeah.
a question to be answered. Like it's not so
Definitely.
much a mismeasurement, it's that there is a component of the algorithm that's just missing.
That's certainly what I think, and at least some of my colleagues think.
Very cool. I mean, I guess it's interesting because even this very simple concept of collecting data that's very, very far away. So like you mentioned, the difference between the black hole at the center of our own galaxy, which is, from a cosmological perspective, like right in our backyard, even though it's still crazy far away, it's closer, versus data collection from kind of far away in the cosmos. This concept that's sort of counterintuitive to non-physicists, that not only are we looking at something far away, but by definition, something far away is a long time ago.
Mm-hmm.
And that's a like the idea of a quote light year, or just the concept of how space and time are linked in that way, I think is something that is often forgotten, especially when we talk about the public communication of science, because we speak of the cosmos often only in a geometric sense and not often in a temporal sense.
Yeah, I completely agree with you. The light that we collected in our telescopes from the center of our galaxy, which you said in a cosmological sense, it's in our backyard, it was emitted 26,000 years ago.
Wow.
So what we're collecting now is what our black hole was doing 26,000 years ago.
And for most of your research, that's like yesterday.
That's yesterday.
Yeah, that's like not even that long ago.
Yeah, because 26,000 versus, for example, the nearby galaxy cluster. Again, we call it nearby. We call it our cosmic neighborhood, the M87 galaxy in the Virgo cluster. That's millions of years for light to reach from there to us. And then when you look farther away from us and you look at galaxies that, maybe that look like us, but we're seeing them as they were billions of years ago. So it is absolutely true that geometry, because we're talking about such vast distances, also maps to the history. And as you're looking farther away, you're looking farther back. So we get information from them, but how they were a while ago. And that way we can also construct the chronology of the universe and not just the geometry of the universe.
Right, right. And so I'm curious in terms of this image. I keep calling it an image, but it's so much more than that. It's like all this data combined in a visual representation. Uh, when we're looking at basically, we're physically looking at a supermassive black hole.
Mhm.
What percentage, I always ask questions like this, what percentage doesn't make any sense. I'm always asking for like weird ballpark, personal, kind of subjective things. But how much of this was an exercise in can we do it, and how important will this be for kind of humanity to be able to kind of get around? And how much of it is like, this is fundamental to our science. If we didn't have this image before, there's so many things we wouldn't understand. I guess not to minimize it, because obviously this is breathtaking and incredible, but it's like the tip of the iceberg when it comes to the actual science involved, right? And I think sometimes we don't realize that when we see an image.
That is absolutely true. I mean, I wouldn't be able to tell you what percent of it is can we even do it, and what percent of it is what are we going to learn from it. But coming back to this theme that is at least central to my career and certainly to some of my colleagues, can we break things? Can we push our experiment to such an extreme that we either see new phenomena or we confirm that the way we describe things, our mathematical and physical framework for describing our universe, still works? I was very much hoping that it would be in the let's break it side of things. I was not. So I, it's a complex system. It's a hard experiment, hard observation. But despite all of that, there was a chance, and maybe there still is a chance with different future observations, that we see something that is qualitatively different than what we expected. And that would have been quite amazing too. Certainly confirming that the theory of gravity or plasmas, etc., work in such extreme settings, and the prediction that there is this mathematical singularity and it has these certain behaviors, and we can tell you exactly what it can't be. We ruled out quite a bit of alternatives by looking at but by looking at the Event Horizon Telescope images. So that's all valuable. I mean, I'm not sad about it or anything, but I think I would have been a little more excited if we broke something.
Yeah, and I also think about this idea of, oh, like, who am I remembering right now? She was Carolyn Porto, and how important it was for her on, I think it was Cassini. I could be misremembering, to say like, put a damn camera on there. Like, what are we doing? Why aren't we taking images? Because
Yeah.
and we think about these incredible stories, Andy Weir's The Martian, and these stories about the kind of human ingenuity, the human experience of science, and then the sort of the public saying, I want to continue to fund these things. I want to be inspired and awed by what we understand about the cosmos, but also what's my ROI and what's the utility? And this like super complicated economic and emotional and psychological and sociological algorithm that goes into doing science. And sometimes something as simple as a picture, just a
Yeah.
picture, can
Yeah.
communicate to people in a way that like just goes to the heart of their humanity.
I agree. I mean, we certainly developed a ton of technology along the way. We developed a lot of computational techniques that are applicable to other areas of science. We developed observational techniques. Um, but ultimately, what it comes down to is we as humans feel proud that we were able to get an image of something that is so small, so far away, so weird. Um, and now we have a visual of what that environment is like. And the younger generation is seeing this, our students are seeing this, and they're thinking anything is possible. I mean, it's this excitement of discovery. So that's the social return, I think, that you're talking about, which I certainly value very much.
How do you, this is, I'm going to get a little philosophical with you, but how do you, as somebody who, has been living through these revolutionary changes, and of course, we could go back and say that about any era of science, there were these revolutionary changes and these deep insights. And, before this time, we didn't even know that that existed, or we didn't even have the tools to explore whatever. But how do you, when you're working with students or when you're looking at younger generations of sciences, sort of find that balance between exactly what you were just talking about, you know, students saying, well, anything's possible. Look at what we've done up until now. And almost like the cynicism of like, oh yeah, there's a picture of a black hole. Cool. Like when somebody like is born into all of this incredible knowledge and sort of, I don't know, there's such a risk that we can so easily take for granted all of the hard work and all of the ingenuity that went into getting where we are today.
That's true. I think it's hard to appreciate how long scientific journeys take and
Mm,
how much effort goes into it. You think, okay, so and so did one thing, or like they developed something in their lab, or saw a new phenomenon, etc. There's on average like decades of work
yeah.
behind those, and that's hard to communicate. Um, at the same time, I'm actually very grateful and pleasantly surprised by how excited everyone that I cross paths with is with the outcome. I mean,
Hmm.
they may not see the 20 years of work behind it, but they still appreciate, oh my God, we did this as humanity.
Hmm.
And same thing coming out of, a lot of like our quantum labs and our genetics labs and our virus experts. We may not truly understand what, like, all the background that went into it and all the challenges that they faced and breakthroughs that they had to make to get there. But I think um, even then, we have a sense of we understand something today that we didn't last year. So I can only hope that this sense of wonder continues with our younger generations.
Yeah. Well, I guess this kind of takes us on a really natural arc through this conversation. Uh, Before I start to close up, I always close with like these two big picture questions that I ask every single guest on the show so that I can, I don't know. I don't know if I'm ever going to do something with their answers, but for my own kind of interest, I love to go there with individuals. But before we dive into those two questions, I'm curious about your own arc. What is next for you in your career? What questions are you continuing to try to answer, and where are you hopeful that those investigations will go?
I think also by virtue of the position that I just started,
Hmm.
I see the I mean, I'm not sure about an arc. I might still go in different places, but right now I'm dividing my effort and time between making sure that others have the opportunity to do the science that they want to do. And
Hmm.
we have a diverse group of students that are coming up through high school, through their undergraduate programs, and getting interested in science and finding the opportunities to do exciting science. That's one direction that I genuinely value. And for my own career, um, of course, everybody has been talking about a data revolution, and there genuinely is one. The amount and the type of data that we can get and the computational tools with which we can analyze them are just amazing, and they change from year to year. The intersection of astrophysics with computational and data science, I think, is going in a wonderful place. And I'm exploring opportunities of how we can do even better to understand the universe with some of these techniques. So, in my own research arc, if we want to call it that, um, that's the direction that I'm going.
Wonderful. So listen, each week on the show, I have a different scientist or science communicator, science writer, science journalist talking about their area of interest and expertise. And I always close the show by asking them the same two very big picture questions. And of course, the big picture can be in whatever context feels relevant to you. So this can be the big picture for yourself personally, for your community, for your nation, for the world, for the cosmos, because of course this is an area where you spend a lot of time thinking about. But what I would like to know is, number one, when you think about the future, again, in whatever context feels relevant to you right now in this moment, number one, what is the thing that keeps you up the most at night, that you're most concerned about? Maybe there's some pessimism or even some cynicism to these, obviously not very positive thoughts. And then to end on a, I guess warmer note, where are you finding your hope when you think about the future? What are you kind of truly, authentically optimistic about looking forward to?
On the what's keeping me up at night front, what is worrying me? I would have to say the lack of diversity that is persisting in some science and technology fields is
Mm-hmm.
um, is something that I'm quite worried about. It's not that there are no initiatives out there. Obviously, we're trying, but it's been a hard nut to crack. There is a lot of talent out there among the the younger generation, and we're not able to attract them into these careers in science and technology where they could make really wonderful contributions. Um, I think we're lacking a systematic approach or something in our society that is still either putting up barriers or not encouraging enough. So that's something that I would like to change. Some science fields are doing better than others. Physics is not, and yeah, I that's a problem we need to solve.
Absolutely.
On the optimism front, though, I think the a lot of my colleagues and I, when we review applications for certain positions, for postdoctoral positions, PhD positions, we joke with each other that we wouldn't be able to get them because the the young generation is doing so much more earlier on, and maybe not all of that is good. They're also an anxious generation, so maybe we're pushing them too much. But what I want to say is that the pipeline is still there. The students are growing up in the data age, and they're doing things that I didn't even know about until I was in my 20s. And they're 10, or 15. It's just the students are coming more and more prepared. more and more excited. They have different tools. So, in terms of optimism, I know that the future of science is bright as long as our society continues to support it, value it, realize that it benefits us all, and there are wonderful technologies that keep spinning off from all the basic science that we do. I think our future is going to be bright.
Yeah. Ugh. Well, gosh, I want to thank you so much for taking the time with us today, Feryal. I've learned so much from you. I'm so inspired by your words, and I just really appreciate you spending this time with us today.
Thank you, Kara. I really enjoyed it too, and thank you for having me.
Of course, and everyone listening, thank you for coming back week after week. I'm really looking forward to the next time we all get together to talk nerdy.